Good morning,
General
everyone.
request.
Today is lecture number 28 of this heat treatment class, and today's topic is on factors influencing hardenability of steel. So, in the previous lecture, we have already started this very important topic, that is hardenability, and hardenability is obviously an important property of steel because we need high hardness, or we need high strength, or we want our steel should be having stronger property, right? It should be stronger and harder, or having wear resistance, and all these things basically depend upon, you understand, on the formation of martensite. Hmm. How easily martensite is forming in the steel, even if we are not quenching the steel, or even if we are not cooling the steel at a faster rate from the austenitic temperature, we are forming martensite. So that defines basically hardenability. So what are the factors? Already we have discussed about many factors like grain size of the austenite phase, the dimension of the steel, whether it is thicker or thinner, and also we have seen the chemical composition like weight percentage of carbon, or weight or amount of alloying elements present, right? So these things basically influence the hardenability, right? So first one is okay, how to say a given steel is having good hardenability. Uh, How suppose I will hand over you a steel, and I will tell you that, can you tell me this steel is having good hardenability or it is having poor hardenability? So obviously the first thing you have to do is what? You have to take the steel and you have to take the steel to the austenitizing temperature. That means you have to convert the entire initial microstructure into austenite phase, and it should be homogeneous one, right? And after you have to cool it. It depends. You can give quenching, you can give slow cooling, you can give intermediate cooling, and you can check the microstructure simply. And you have to check the microstructure means you have to check the microstructure starting from the surface to the center. You can make many cross sections, you can cut it into many pieces, you can do sectioning of it. You can take sections from different portions starting from the surface, then at the intermediate portions, then to the center portions, and you have to check the microstructure, and you have to check whether martensite has formed everywhere or not. Basically, if martensite have formed everywhere, that means martensite have formed on the surface also, in the intermediate portions also, and at the center also we have martensite. That means I can say my steel, or the steel you have received from me, is a good hardenability. It is showing good hardenability characteristics. And uh, suppose the steel is somewhat thicker, it is somewhat of higher dimension, it is completely thicker steel, the thickness is very high. So in that conditions, obviously the cooling rate will be not same everywhere, right? The cooling rate will be faster obviously at the surface, but at the center it will be slower, right? Because you understand the cooling rate also influence the decomposition, right? Decomposition of austenite to martensite, or decomposition of austenite to perlite will change, right? Depend upon the cooling rate also, right? One is the transformation temperature, and the cooling rate also affect the transformation, or what kind of transformation product you will get, that will affected by the transformation temperature, whether it is higher or whether it is lower, or it also affected by the rate of cooling, whether your cooling rate at a very slow rate, fast. So since you understand, you if you have a very high thickness of steel, the cooling rate will be different at different section of the steel. So in that condition, suppose you will get 50% martensite and 50% perlite, that is also fine. At the center I'm talking about, that means obviously at the surface you will having 100% martensite, but at the center if you have 50% martensite and 50% perlite, that is also fine. You can say it is of good hardenability characteristics, right? But if the amount of martensite will be below 50%, then I cannot say it is showing good hardenability characteristics. But condition applied, the thickness is important also. That's why I told the factors influencing hardenability is the thickness also. Thickness also plays a good role. If you have a very high thickness, then you cannot achieve good hardenability characteristics up to the center, right? Because center will be having maximum amount of perlite, or you can have 100% perlite, and perlite is a softer phase compared to that of martensite, right? So this is the concept. Then how this is feasible that upon relatively slow cooling we can harden a steel or achieve good hardenability in a steel. So you are doing slow cooling. Relatively cooling rate is very slow, even if you want high hardenability or good hardenability in the steel. So the answer is simple. So I can write the factors or parameters which shift the nose of the TTT, or here if you are doing continuous cooling you can use TTT, CCT. The factors or parameters which shift the nose of the TTT or CCT curve diagram otherwise towards right side. Helps to achieve good hardenability, right? So if you want good hardenability in characteristics in your steel, then there are certain factors which basically shift the nose of the CCT curve or TTT curve towards right side that will help you to achieve good hardenability. It simply means what? Obviously by adding alloying elements. That means we understand, except cobalt, basically we understand other alloying elements basically shift the nose of the C curve of the TTT or CCT diagram, right? So that means even if we are cooling the steel at a slow rate, we can achieve good hardenability. Yes. So you people have understood. So that means I can write by adding alloying element, by adding alloying elements, except cobalt, the nose can be shifted towards right. So open relatively slow cooling rate, it can form martensite. So in other words, what I can say in terms of this critical cooling rate. So critical cooling rate will become slow or high if you are adding lot of alloying elements. Slow. Yes, obviously the critical cooling rate will become slow because the nose is moving towards right side. So if you draw a cooling curve, it will not easily touch the nose of the curve, because once it will touch and it will cross the nose of the curve, then transformation of this austenite to perlite may happens. Right? So we have to suppress the perlitic formation also. Okay, anyways. So next is factors influencing hardenability. So first is the effect of austenite grain size on hardenability. So this is one of the important factors, that is austenite grain size, which affects the hardenability. Right? So we understand we have a initial microstructure and we are converting the initial microstructure to the austenite first, right? So in maximum heat treatment, our first job is to take the steel to the austenitic temperature to make it homogeneous austenite, right? And we understand austenite basically start nucleating at the interface of ferrite and cementite if present, right? So more is the surface area, more is the formation of, more is the rate of nucleation of this particular thing. So, how austenite grain affects? Basically, we can have smaller austenite grain, we can have bigger austenite grain, or bigger, or you can write coarser, technical term. So, if we have smaller austenite grain, the hardenability will be poor. Will be poor. But if we have coarser austenite grain, bigger austenite grain, we have good hardenability, or we can have high hardenability. Good or high, you can write. So why this is so? You understand? If we have small austenite grains, that means we have lot of grain boundaries, right? And if we have lot of grain boundaries, we understand we have lot of easy diffusion path. Diffusion will be easier, and perlytic transformation is a completely diffusion based transformation. If diffusion will be easy, then perlite formation will be easy. That means nucleation and growth of perlite will be easier, right? So you understand now, if we have smaller austenite grain size, we have lot of grain boundaries, and lot of grain boundaries means we have easy diffusion path. And if we have easy diffusion path, then rate of nucleation and growth of perlite will be easy and faster. So if perlitic transformation will be easier, perlitic formation will be easier, that means austenite will easily transform into perlite. So which suppress the formation of martensite. Right? So you understand similarly, if we have a coarser austenite grain size, that means we have less number of grain boundaries, or very minimum grain boundaries we have. So that means perlite transformation will be suppressed, martensite transformation will be easy. So in one word I can write, nucleation, growth, easy. It suppress of austenite to martensite. The same answer you can write here. Then next question: why it is not recommended to have coarser austenite grain size to achieve hardenability, good hardenability? So the conclusion, what you got? The conclusion you got is what? If we want a high hardenability characteristics in the steel, then we have to go to a high temperature, right? Because if you go to a high temperature, that means we'll have a coarser austenite grain, and that coarser austenite grain, if we have, then transformation of austenite to martensite will be easy, because the suppression of austenite to perlite transformation will be there, right? Due to coarser grain of austenite size, right? But this is basically not recommended. This is not recommended due to many reasons. So what are the reasons? I can mention here the reason behind this. So one of the reason is ductility will be reduced, because hardenability will be more, means ductility will be reduced, toughness will be reduced. These are very good properties: ductility, toughness. Basically toughness is one of the important properties. So ductility will be reduced to a large extent, toughness will be reduced, and cracks may generate due to high hardenability. So the conclusion is what? We basically do not prefer to have coarser austenitic grain, even if we want high hardenability. Even if we want high hardenability, we try to keep the austenite grain optimum or smaller one, because if we go to a high austenite grain size and we do hardenability, we can achieve high hardenability, but that will deteriorate other properties, like ductility will be reduced, toughness will be reduced, and cracks may generate, which is not beneficial actually. Cracks may generate.
Hello, sir.
Yes.
Sir, grain size course ductility reduce କାହିଁକି sir?
Here we are talking about the formation of martensite. So you understand when martensite form, it is very hard and brittle. So what will happen to the ductility?
Decrease.
Obviously, because we are talking about hardenability, and hardenability is completely relates to the formation of martensite. And if you are having coarser grain size, you are having high hardenability. That means martensite is forming completely. It is forming. It is easily forming. And if martensitic structure will be there, hardenability, the ductility will be reduced. That is the answer. It is okay now?
Okay, sir.
Okay.
Sir,
Yes.
sir, if we have problem with both the fine grains and coarser grains, then
Hmm.
sir, what we can do? When
I told
muddy major grain size of yes,
you
sir.
can have a optimum grain size so that you can maintain both properties. You can maintain toughness also. You can maintain hardness and strength also. See, if because you understand, strength and ductility are always opposite. In if you want to always increase the strength, the problem will be what? The ductility will be reduced, and that will affect the toughness property. And obviously, the final service application is important because you want, suppose you, for example, car bodies, right? In car bodies, you always want, you should have high toughness, you should have high strength also, right? You should have high strength and high toughness also. So that is why you have to maintain a fine grain anyhow. It is okay, you have to maintain a fine grain over there. If you are not maintaining fine grain, if you are maintaining coarser grain, so ductility will be increased, toughness will be decreased. But in other way, if you are increasing high strength, the chances that the toughness will be also reduced. So depending upon the applications area, actually we want always. See what, suppose application area wants high wear resistance, right? So obviously you have to form martensite, and then if the martensite will be harder also, brittle also, we don't have any problem. But if there is impact loading will be there, sudden loading will be there, then that leads to the failure because it cannot absorb a lot of energy on the impact. So in that case, we should have high wear resistance as well as we should have high toughness. Right? If only wear resistance is important, then if martensite will be brittle, we have no problem because we have to prevent only wear. We do not consent with the toughness there. But so depending upon the service, properties are always important. You have to look into the service area first. In that service applications, what we need, what kind of property is essential, whether toughness is only important or whether strength and toughness is important, whether hardness and toughness is important or where only hardness is important, or whether we have toughness and strength and wear all are important, right? Or where we want a high fracture toughness also, because you understand during service also cracks may generate in the materials. So in that case we need high fracture toughness because already crack is present, we don't want the crack will propagate. Here we want some ductility because you understand if the crack will remain blunt, right, it cannot easily propagate. But if the crack will remain sharper, right, or a longer crack will be there, it will easily propagate upon impact loading. I think your concept is clear right now.
Yes, sir.
Yes. So you have to remember, whenever you are putting a material, for example, steel into any applications, first of all, you have to check the environmental conditions. What is the condition is there? And after checking the condition, severity of the environment, then you have to look into whether the property, what are the property needed for the applications. After getting the properties, you have to check whether your steel or whether your material can sustain over there or not. Right? So these are the things. Okay. So now next one is the effect of carbon. So effect of carbon is also important to decide the hardenability. So how we'll see that soon. So you can see hardenability of a pure iron carbon alloy. So if we have a pure iron carbon alloy, means you can understand there is no other alloying element is there, only iron and carbon is there, or you can call it is a plain carbon steel. So plain carbon steel have poor hardenability characteristics. This is a relative. I am comparing. I am not saying directly. I am comparing the plain carbon steel with alloy steel. That's why. So poor hardenability. Even if you are doing quenching, you cannot get martensite everywhere sometimes because of poor hardenability. Why? Because alloying elements are absent. And you understand, if alloying elements are absent, the the nose of the TTT curve or CCT curve is not shifting towards right. So we cannot have high hardenability, right? So this is the answer. And similarly, hardenability of commercial grade plain carbon steel. So this is important because you understand, if you look and carefully look into the chemical composition of commercial grade plain carbon steel, if I am saying, it is only carbon is there as an alloying element, right? But commercial grade, if I am saying, that means anyhow we have certain amount of manganese in the, or some certain amount of impurity element will be there. Basically, manganese is one of the impurities which will always there in the plain carbon steel. So you understand, to show comparatively good hardenability. Compared to this pure iron carbon alloy, right? You understand, because pure iron carbon alloy means only carbon is there, but now commercial grade plain carbon steel means some manganese content may be there. You can write in bracket, I am writing commercial grade plain carbon steel contains some alloying elements, contains some alloying elements like manganese, and other elements. Anyways, so next is hardenability of hyper-eutectoid steel. So if we are talking about hyper-eutectoid steel, means you understand it is the carbon content is greater than 0.8, right? So basically, beyond 0.8 percentage carbon in steel, that is hyper-eutectoid steel, the hardenability decreases. What is the reason? The austenite in this case is austenitization, basically. Sorry, austenitization is basically carried out in two-phase resin. If you remember, if we have a hyper-eutectoid steel, we basically prefer to do austenitization in the two-phase resin, where austenite will be there, sorry, cementite will be there, and austenite will be there, right? Two-phase resin. No, that means it is below ACM or above A1. So due to presence of austenite plus cementite below ACM, certain conditions, transformation to austenite is partial. A small amount of cementite remain undissolved. The undissolved cementite restrict the hardenability. So you understand? The reason is what? Austenitization. Austenitizing is carried out in two-phase resin. Austentation is carried out in two-phase resin. That is below ACM and above A1. Right? That means in between the lower critical temperature and upper critical temperature, that is ACM. Right? So some undissolved cementite will be there. Carbide, that is iron carbide, is still there, which prevents, which reduces the hardenability. This is the answer. Next one is the effect of alloying element on hardenability. So what is the, obviously we have already discussed this one, effect of alloying element on hardenability. So except cobalt, other alloying elements see present, they basically shift the nose of the CCT curve or TTT curve towards right side. So even we are doing relatively slow cooling, we can easily get martensite. So we can have a good hardenability characteristics. So that is the answer. So presence of alloying element except cobalt, role and condition to achieve good hardenability. So one you understand one point is the shifting of the nose of the TTT curve or CCT curve towards right. Hmm? The nose of the curve towards right. That is the answer. Second answer is what? Okay, fine. Then next here it is written condition to achieve. So it doesn't mean that you have alloying elements in the steel except cobalt and you are getting high hardenability. That is not the thing. The other important point you have to notice is whenever we are doing austenitization, this austenite should be homogeneous. Austenite must be homogeneous. If it will be not homogeneous, the austenite, if some alloying elements are there which form any carbides, nitrides and all, right? You understand, obviously, if there are any ferrite stabilizers like chromium and all, or niobium, vanadium, titanium and all, they form strong carbides and they are not easily soluble in the austenite phase. And even if they are soluble, the solubility is very slow and all. So if the austenite will be inhomogeneous, then hardenability will be poor, right? So in other words, I can write inhomogeneous austenite inhomogeneous austenite reduces the hardenability of the steel. The reason you understand, because of the strong carbide nitrides or any non-metallic phases will be there which are not soluble easily, or it is taking time. So austenite become inhomogeneous. Then role of cobalt. Cobalt, already I told you, cobalt is the exception which do not shift the nose of the TTT curve, CTT curve towards right. So if cobalt will be present, what I can write? Here I can write first thing is it do not shift the curve, shift the nose of TCCT. And what happens also, due to which it promotes the nucleation perlite, nucleation growth of perlite and growth. So you understand what I can write? Martensite transformation suppressed because perlite formation will be there, so martensite transformation will be suppressed. So if cobalt will be there, if you have a steel containing only cobalt, it will never shift the nose of the TTT curve towards right, right? So that we cannot easily get a martensite upon slow cooling. That is one part. Second part is this cobalt also helps in the nucleation growth of the perlite phase, which is a that is a diffusion based transformation. So if diffusion based transformation will start, martensite formation will be not easy, or it will be difficult, or it will be suppressed. This is the answer. Now presence of strong carbide forming elements. So presence of strong carbide elements like chromium is there. So you understand, if chromium will be there in more and more amount, so what will happen? Chromium carbide formation will be there, and if chromium carbide formation will be there, so what will happen? The austenite form will be inhomogeneous basically, because it is taking some time to dissolve, or to get homogenization it requires more time, right? You have to go to a high temperature also to make it soluble, because cementite or iron carbide is easily soluble above 650 like that, but to dissolve other carbides like chromium carbides. If vanadium niobium, it requires very high temperature. It takes very high temperature to make it soluble. Or once it will be soluble, it takes more time to get homogenized also. So presence of strong carbide forming elements like chromium suppress the hardenability or make the hardenability become poor. So poor hardenability. So let me show you a image. So this is an image. Let me write the reference here. Reference is heat treatment principle and technique from TV Rajan. CP Sharma and Ashok Sharma. So if people just look at this one and tell me what is happening. Let me see you can answer.
So with increase in chromium percentage, hardness increases.
Hardness increases. Okay, fine. That is the only part you can able to see. Anything else? What
So
we are
the
talking about?
hardness is varying from top to center and then increasing from center to the other end.
That is fine. That is you are talking about the depth and distribution of hardness. Okay.
Yes.
But tell me on the basis of chromium, what is happening? As someone told, the hardness is increasing, obviously, because carbide will be there, so the strength will increase. They prevent the motion of
Addition of
surface.
2% chromium decreases the hardenability.
Okay, fine. So yeah, other word you can see this first one when there is 0% chromium in the carbon steel, you can see the variation of hardness from the surface to the center is not so high. It is nearly uniform or close to that, comparable. But again, if you have 0.5% chromium, it is somewhat comparable. At the surface hardness and the core hardness or the center hardness is comparable. But the moment you are increasing the chromium to 2%, you can see there is a huge difference. The hardenability at the surface and hardenability at the center is there is a much difference. If you draw a straight line connecting this, you can see there is a much gap, right? Similarly, if you increase more chromium percent, again you can see there is a much difference. So that means with increasing in the chromium percent, the hardenability is decreasing, right? Because the depth and distribution of hardness is not same everywhere because of formation of more chromium carbides or strong carbide forming elements, which are basically not dissolving into the austenite easily. And even if they are dissolving into austenite easily, not easily, difficult to dissolve into austenite, the homogenization of austenite is not happening easily. It is taking much time. So this is the answer. Now there is a concept here, as I told, solubility temperature of certain strong alloy carbides. So as I told, they are ferrite stabilizers which basically form strong carbides. The best example is the niobium carbide and vanadium carbide. These are the and titanium carbide also. They are very stable carbides. They do not easily get soluble in the austenite phase. They require very high temperature. So here basically we are talking about niobium and vanadium. If you remember, whenever in that part when we are talking about HSLI, high strength low alloy. That is the concept now, because we are getting finer grains over there. The strength is high, toughness is also good. It is also providing good corrosion resistance. Anyway, so niobium carbide and vanadium carbide. It is 1150 degrees centigrade. Okay, anyways, degree centigrade. and this is 1050. That means you can understand this niobium carbide is still stable up to this temperature, and vanadium carbide is still stable at this temperature, right? But basically we do austenitization at a temperature of suppose 950 degrees centigrade or 850 degrees centigrade or 900. That means even at austenitizing temperature, this carbide will be still there. So what will happen? If they will be still there, they will prevent the growth of the austenite phase. So austenite grain formation will be very smaller, finer austenite grain will be there. So in the conclusion part, you can write what? If finer austenite grain will be there, so there is a suppression of formation of austenite phase. Formation of martensite, because they are finer grain. Already we have discussed that if finer grain will be there, austenite grain will be there, the hardenability will be poor. So that is the answer you can write. Then effect of this carbide on homogenization of austenite phase. So what we talked about the solubility here, that means. But in this case, what happened to the homogenization of austenite? Yes, homogenization of austenite will be slow, right? So temperature effect, if you look, this carbide will be still stable at high temperature. They will not become soluble. The second one is solubility in austenite. It is sluggish. Very slow. They are very this carbides basically takes much time to get soluble because of diffusion. The diffusivity is very low of these elements. dt of these elements. Then comparison between hardenability of plain carbon steel and steel with vanadium. So this is a question from my side. Can you people tell me, if you have a plain carbon steel, on the other hand you have a vanadium steel, the austenitizing temperature is fixed for them. So in which case you can get high hardenability, or in which case you can get low hardenability, and why? Here we basically want to compare between the plain carbon steel and steel containing vanadium. This is a very critical question. In earlier part, we have seen if we have a plain carbon steel, that means alloying element are absent. The nose of the TT curve will not move towards right, so hardenability will be poor. Already we have discussed that. And again, we have discussed here is vanadium is there. Vanadium forms strong carbides, which is not easily soluble. And if it will be soluble, but homogenization will be not easier, it will take time. So hardenability will be poor. So now there is a very good confusion between them. So how you can compare this one? Where you can get high hardenability, where you can get low hardenability, or you will get same hardenability. You have 10 seconds to think. Okay, your time is over. The thing is what? Let me show you this one. This can be explained with the help of this one. You can see this is also taken from a reference. Just look at this one and tell me in which case you are getting high hardenability and in which case you are getting low hardenability. Here you can have GS means grain size number. Grain size number is there. The austenitizing temperature is there. This image is showing for plain carbon steel. This image is showing for vanadium steel. So in which case you are having high hardenability. and we are comparing same. We are taking same diameter of steel, 25 mm. Here also 25 mm diameter, and you can see austenitizing temperature is 980. Here also 980. You are having 900. Here also we are having 900 nearly, or 940. Here 940 is there. Sorry, this is 940 and this is 940. Here you have 780. This one. Here you have also 780 here. This one 780. 900 here, and here you have 900 here. The temperature condition is same, diameter of the steel is same, but this steel is only plain carbon, this steel is vanadium containing steel. And these are grain size number 1 to 2, grain size number 2 to 3, grain size number 4, 3 to 4. Here grain size number is 4 to 5, 6 to 7.
Sir, in vanadium containing steel,
Yes. In vanadium containing steel, you are having high hardenability. Okay. Anybody want to speak anything else?
Sir, plain carbon still have high hardenability.
Plain carbon steel have high hardenability.
Sir, in
Okay.
carbon steel, sir, at the same temperature, we are getting high hardenability in steel.
In high
In
hardenability?
carbon steel, at same temperature, 780, the
Yes, yes.
hardenability is more in steel
Very good, very
than.
good. Amiz, you are right, and Panda also you are right, because you can see if you people, I think you people have forgotten the graph. This is hardness value, and this is the depth. Hardness value, and this is the depth. If the curve will go more down, that means at the center you are having more perlite, less martensite, right? So you can see the curves. You compare the curves. You compare the curve of 780, for example, this one. 780 degrees centigrade. You can see the curve is up to this. This is the hardness value 40, for example, at the center. But you can see at 780 for vanadium, at the center the hardness is less than 40. It is nearly 35 or less than 35, right? So what is the answer? The depth and distribution of hardness is greater here, but it is less here. This is uniform hardness at the surface and at the center. But here there is more change in hardness from surface to the center. Similarly, suppose you compare this one 900 degrees centigrade, and you compare this one 900 is this one, this curve. You can see there is a fall of hardness, more fall of hardness in case of vanadium at the center. It is how much? Suppose it is 40, 42, like that. But here at the center for 900 it is 55. You can see. So there is a more decreasing in the hardness in case of vanadium at 900, but at 900 there is less decreasing in the hardness, that is 55 only. So obviously that means hardenability is higher in case of plain carbon steel. Okay, can you tell me what is the reason behind this? Already I have given you some hints here. What may be the reason? Patnaik, can you answer this one? What is the reason behind this? Susri Debasmita, can you answer? What is the reason behind that plain carbon steel have high hardenability here if we compare it with the vanadium steel? Shweta, you want to speak something on this?
Yes, sir.
Can you tell me the reason?
No, sir, I don't know.
Because of grain size, I am writing. Now, can you explain? Just look at the grain size. At 900 degrees centigrade, what is the grain size? Here and here.
Sir, because grain size is finer
In which
and
case?
in vanadium it is coarser. In carbon steel.
In carbon steel, it is finer or coarser? At same temperature.
900. Sir, it is coarser.
Coarser in case of?
Coarser in case of carbon steel.
Yes, very good. So how you can how you got
And
that? How you got that? By looking at the figures?
yes, sir.
Can you elaborate? Can anybody want to elaborate this one? How by looking at the figures, you can say which one is coarser or finer? Okay, fine. You can see it is grain size 4, 5, but here grain size 1, 2. That means 4, 5 means grain size number is bigger, so grain is finer. Here grain size number is small, so grain is coarser. So because of vanadium, we have vanadium carbide, and vanadium carbide prevents the grain coarsening. So grain size will be finer, so hardenability will be poor. But here in case grain size will be bigger, so hardenability will be higher. So this is the answer. Okay, last part, the role of non-metallic inclusion in steel in hardenability. So non-metallic inclusions, if you remember, it may be your oxides, or it may be sulfides, or it may be your silicates, or, complex oxides like that. So they basically they prevent the coarsening of the grain. So once they prevent the coarsening of the grain will remain finer. So if we have very fine inclusions, non-metallic inclusions like below 10 mm, 10 micrometer or 10 micron, and there is a uniform distribution of these non-metallic inclusions like oxides, sulfides, silicates, or complex oxides like that. So there is a refinement in the grain size. So what will happen if the grain size will be refined, smaller grain size, hardenability will be poor, like that. You can answer poor hardenability. And second one is role of boron on hardenability. Actually, if boron amount is present in very less amount, you can see very minimum, hardenability will increase. Hardenability will increase. Why? Why? Because the answer is this boron get dissolved into austenite phase, and they get segregate along grain boundaries. So what happens to the boron? This boron, when added in a small amount, they become soluble in the austenite phase, and they get segregate along the grain boundaries. Right. So once they get segregate, they prevent the formation of pro-Eutectoid ferrite. So once pro-Eutectoid ferrite is prevented, then that will help in the hardenability of the steel. So okay, this part is clear. So I'll end the lecture here.